Hey everyone, Mark Rober here. Today we're diving into the fascinating world of storage classes in C programming. This is a fundamental concept that every programmer should understand. Think of storage classes as the blueprints that tell the computer where to store your variables and how long they should stick around. They define the scope, lifetime, and visibility of variables. They're like designated parking spots for your data, each with its own rules and perks. Just like how a parking spot can be reserved or open to everyone, storage classes have their own unique characteristics. Why should you care about these storage classes? Well, they play a crucial role in how your program runs and performs. Understanding them can make your code faster, more efficient, and easier to debug. It's like having a well-organized toolbox where you can quickly find the right tool for the job. It's like organizing your tools in a workshop. The right tool in the right place makes all the difference. This organization can save you time and effort in the long run. In the upcoming sections, we'll break down the four main storage classes: auto, register, static, and external. Each of these has its own specific use cases and benefits. We'll keep it simple, engaging, and full of real-world examples so you can master these concepts in a flash. By the end of this series, you'll have a solid understanding of how to use each storage class effectively. So buckle up and let's explore the fascinating world of storage classes together. Get ready to enhance your programming skills and take your coding to the next level. First up, we have the auto storage class, the default setting for most variables in C. It's like the standard parking spot you get without asking. When you declare a variable inside a function without specifying a storage class, it automatically becomes an auto variable. Auto variables are stored in the computer's RAM, which is like its short-term memory. They're created when the function starts running and disappear once the function finishes, just like your notes on a whiteboard. This temporary nature of auto variables makes them perfect for storing values that are only needed within a specific function. It's like using a scratch pad for calculations. You jot down what you need, use it, and then erase it. In the next section, we'll explore the register storage class, which offers even faster access to your variables. Stay tuned. Now let's talk speed. Speed is crucial in computing, and optimizing it can make a significant difference in performance. The register storage class is like the express lane for your variables, giving them VIP access to the CPU's registers. This means they get processed much faster than usual. CPU registers are like the CPU's personal high-speed memory, much faster than RAM. Think of it as the CPU's own private workspace where it can quickly access and manipulate data. By declaring a variable as register, you're basically requesting the compiler to store it in a register if possible. This is a way to hint the compiler to prioritize speed for that variable. This can significantly speed up your code, especially for frequently accessed variables used in calculations or loops. Imagine the boost in performance during intensive computations. However, there's a catch. Registers are a limited resource, so the compiler might not always grant your request. It has to make decisions based on the overall needs of the program. It depends on factors like the number of available registers and the variable's data type. The compiler evaluates these factors to decide the best use of registers. Also, you can't get the address of a register variable using the address of operator, and. This is because the variable is stored in a register, not in regular memory. It's like having a secret stash that you can access quickly but can't tell anyone about its location. This makes register variables unique and powerful, but with certain limitations. In the next section, we'll delve into the static storage class, which offers a different kind of persistence for your variables. Stay tuned to learn more about how it can benefit your code. Moving on to the static storage class, think of it as a long-term memory storage for your variables. Unlike auto variables that vanish after a function call, static variables retain their values throughout the program's execution. They are like notes etched in stone. They stay put even when the function that created them is long gone. This makes them useful for storing values that need to be remembered across multiple function calls, like counters or flags. Static variables are stored in RAM, just like auto variables. However, they have a longer lifespan and are initialized only once at the beginning of the program's execution. In the upcoming section, we'll uncover the external storage class, which allows you to share variables across different files in your project. Section 5. Unveiling the external storage class. Last but not least, we have the external storage class, the bridge between different files in your C program. It allows you to declare a global variable in one file and access it from other files. Imagine you have a large project with multiple C files. Instead of passing variables back and forth between functions, you can declare them as external in one file and use them in others. To use an external variable, you need to declare it using the keyword in the files where you want to access it. This tells the compiler that the variable is defined elsewhere, and it should look for it during the linking stage. In the next section, we'll solidify our understanding of storage classes with some illustrative examples. Get ready to see these concepts in action. Section 6. Illustrative examples of storage classes. Let's bring the storage classes to life with some simple examples. Understanding these examples will help you grasp how different storage classes function in various scenarios. First, consider the auto storage class. This is the default storage class for local variables. Imagine a function that calculates the area of a rectangle. This function might look something like this. Int calculate area, int length, int width. Int area, equals sign length asterisk width, return area. Here, the variable area is an auto variable. It is local to the function and only exists during the function's execution. It's created when the function is called, used to store the calculated area, and then disappears once the function returns the result. This temporary existence is a key characteristic of auto variables. Now, let's look at the static storage class. Static variables, unlike auto variables, retain their value even after the function exits. Suppose you want to count how many times a function is called. You might write a function like this: void count underscore calls. Static int call underscore count equals sign 0. Call underscore count plus plus. Print function called %d times, done, call underscore count. In this case, the variable call underscore count is declared as static. This means it is initialized only once and retains its value between function calls. It retains its value between function calls, allowing you to track the number of times the function is invoked. This is particularly useful for functions that need to remember their state between calls. For the external storage class, imagine you have two files, data.c and main.c. In data.c, you declare a global variable // data.cc int global underscore count equals sign 0. Then in main.c, you can access this variable // main.c hash include extern int global underscore count. Int main, printf global count %dnn global underscore count, return 0. By declaring global underscore count as extern, you can use it in main.c even though it's defined in a different file. This allows for sharing variables across multiple files. These examples demonstrate how different storage classes cater to specific needs in programming. Each storage class has its own unique properties and use cases. Understanding these differences is crucial for writing efficient and effective code. In the next section, we'll explore the practical implications of understanding these concepts. Stay tuned to see how these storage classes can be applied in real-world programming scenarios. Section 7. Practical implications of storage classes. Understanding storage classes is crucial for writing efficient and well-structured C programs. By choosing the appropriate storage class for your variables, you can optimize memory usage. Auto variables help free up memory when no longer needed, while static variables provide persistence when required. Improve program performance. Register variables can speed up critical code sections by minimizing memory access times. Enhance code organization. External variables facilitate modularity by allowing you to share data across different files. Moreover, understanding the scope and lifetime of variables based on their storage classes is essential for debugging and preventing unexpected behavior in your programs. In the next section, we'll discuss some factors to consider when choosing the right storage class for your variables. Section 8. Choosing the right storage class. Selecting the appropriate storage class depends on how you intend to use the variable in your program. Here's a quick guide. Auto. Use for local variables within a function that are only needed temporarily. Register. Consider for frequently accessed variables in performance-critical sections, but remember that the compiler might not always grant your request. Static. Choose for variables that need to retain their values across multiple function calls within the same file. External use for global variables that need to be accessed from different files in your project. Remember to weigh the trade-offs between memory usage, performance, and code organization when making your decision. In the concluding section, we'll recap the key takeaways and emphasize the importance of mastering storage classes for efficient programming. Section 9. Conclusion: Mastering storage classes for efficient programming. Congratulations! You've journeyed through the world of storage classes in C programming. We've explored the four main types: auto, register, static, and external, understanding their unique characteristics and use cases. By mastering storage classes, you gain finer control over your variables' scope, lifetime, and storage location. This knowledge empowers you to write more efficient, organized, and maintainable C programs. Remember to choose the right storage class based on your program's needs, considering factors like memory usage, performance, and code structure. With practice and experimentation, you'll become adept at wielding the power of storage classes to your advantage. So, go forth and code with confidence, knowing that you have the tools to manage your data effectively and create exceptional C programs.